This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, good morning everyone. So hopefully today we'll get almost all the way to the end of part 3 of the notes so that we can start part 4 on Thursday, but then on Friday we'll have a look at problem set 4, which is about the application of feedback control to manage the flow of water through a water distribution network that's powered by gravity. Okay, so try to have a look at problem set 4. We'll be looking at that on Friday. So what we've been doing over the last couple of lectures is moving on from thinking about just the stability of a closed loop system towards thinking about performance and in particular potential limitations on what might be achievable. Okay. So within the context of feedback control, we've been thinking about performance in terms of the shape of the sensitivity functions across frequency, okay? And in particular, we've been thinking about the shape of the sensitivity functions across frequency in terms of the shape of the so-called open loop gain, okay? Where the open loop transfer function is just the product of the plant and controller transfer functions. So we've seen that for good reference tracking and input-output disturbance rejection, we need large open loop gain. Okay, and large open loop gain, as we've seen many, many times, so if this is the open loop transfer function lambda, large open loop gain means that the output sensitivity function 1 on 1 plus lambda will be small. Okay, and this is the transfer function from the reference to the error. It's the transfer function from an output disturbance to the output signal that gets measured and fed back to the control system. So if we know that the reference has a lot of energy at low frequencies, we want to make sure that that's small at low frequencies, and that's achieved by making lambda large. Okay, we can make lambda large over a wider range of frequencies just by increasing the gain of it in the same way across all frequencies, which will push the crossover frequency to the right. Okay, so knowledge about where the reference and the output disturbance have energy, which is typically over a low band of frequencies, gives you a lower bound on the crossover frequency. Right? So if we know a reference has and disturbances have energy up to here, the crossover frequency must be to the right of that. Okay, that's what we mean by a lower bound. Okay, so they're not the only things that we're worried about when designing a feedback control system. We want to make sure that the resulting closed loop system is not too sensitive to measurement noise. So a disturbance on the signal that gets fed back from a sensor that measures the output of the plant. Okay, and we want to make sure that we're not sensitive to modelling uncertainty. And we've seen that when the modelling uncertainty is multiplicative, okay, then typically the uncertainty is more significant at high frequency than it is at low frequency. And in order to make the closed loop insensitive to that, we just need to make sure that the complementary sensitivity function, okay, which is lambda on 1 plus lambda, is small at frequencies where the uncertainty is large, which is exactly what we have to do in order to reduce sensitivity to measurement noise. And again, that's often most significant at high frequency. And we make the complementary sensitivity function small at frequencies where we need it to be by making the open loop gain small. Okay, so if we know that these things are significant over a range of high frequencies, then it's saying that in order to get t small, we need the crossover frequency to be to the left of some value. Okay, so these lead to an upper bound on the crossover frequency. Okay. In terms of what the output of the controller is doing, okay, which relates to the interface to the plant, that's, which will be an actuator of some description. An actuator is saturate and they have rate limits and so forth. So you might have to be careful about ensuring that the gain is not too large over certain frequencies, okay? And in particular, we want to make sure that the controller gain is not very large, where the plant gain is small, because that will lead to peaking of the sensitivity function that tells you about how sensitive the controller output signal is to external disturbances entering the loop. So again, these sorts of things provide an upper bound on the crossover frequency, right? Because the easiest way to push the crossover frequency to the right is just increase the gain of the controller everywhere, right? But if we increase the gain of the controller everywhere, we might get peaking in the sensitivity function that relates input disturbances to the control output at frequencies where the plant has already rolled off, which might lead to actuator saturation and rate limit type problems. Okay, so basically control design is about trading off competing objectives, and we manage those trade-offs by separating the competing objectives across frequency, right? So typically this stuff is low frequency, typically this stuff is high frequency. Okay, you can make sure that they're separated, for example, by investing more effort in modelling to make sure that the uncertainty in the model is all at frequencies that are much more significant than the reference or the disturbance, okay? Or you buy a new sensor to make sure that the measurement noise is at a frequency beyond where the reference has most of its energy or where the output disturbance has most of its energy, okay? So, you might not naturally be able to separate these things, right? But by investing more effort in modelling or buying different sensors or different actuators, you can often separate these competing objectives across frequencies. All right. Last time we looked at some limitations associated with the feedback interconnection structure. Okay, they started off with looking at delay, and we saw that delay puts a limit on how high the crossover frequency can be. All right. We saw these so-called interpolation constraints and observed that at open loop poles of the plant or the controller transfer function, the output sensitivity, right, which tells you how sensitive the error signal is to the reference, it tells you how sensitive the output signal is to an output disturbance, will be 0 at the open loop poles. Okay, and that means the complementary sensitivity function will be 1. And we discussed how that could be exploited to ensure 0 steady state error for tracking of step references or rejection of step outputs, okay? By putting an open loop pole at S equals 0. So if we put an open loop pole at S equals 0, that forces the output sensitivity function to be 0 at 0. And if the output sensitivity function is 0 at 0, then it must have this form. It must be the product of S and another rational function, right? Where the degree of the numerator of this rational function will be 1 less than the degree of the numerator of this, okay? And the denominators will be the same, right? This factor S coming out the front corresponds to S being 0 at 0 when there's a pole, open loop pole at S equals 0, okay? And so if we apply a step input at the reference, say, or at the output, then, let's just think about a reference, then the error signal here, which is just the product of the Laplace transform of the reference and the output sensitivity function, will look like this, right? Because S can be factored like this, the S's cancel out, and you're left with this being the Laplace transform of the error signal. And if the closed loop is stable, then this S hat, which has singularities at the poles of the sensitivity function, that they will all lie to the left of the imaginary axis. And so we know that the region of convergence for the Laplace transform of the error signal will then be a right half plane that contains the imaginary axis. And that tells you that it's a signal that decays to zero as exponentially, in fact, as time goes to infinity. All right? So we're going to focus a bit more on this now to see how it can be exploited to ensure zero error tracking or zero error disturbance rejection for more sophisticated signals than steps, okay, today, all right, which will lead us to something called the internal model principle, which is a really important principle from the perspective of control system design. All right. Last time we saw how these sorts of interpolation constraints lead to these integral constraints, right, which give us guidelines about where to set the crossover frequency, right, relative to the open loop unstable poles. Okay, and you don't always have open loop unstable poles, but if you do, you need to make sure that the loop gain is sufficiently high at frequencies that correspond to the fastest open loop unstable poles. Okay, and similarly, we arrived at this rule of thumb for how the loop gain should be sufficiently small at frequencies that correspond to the slowest open loop zeros in the right half plane, the slowest being the ones that are closest to the imaginary axis. And this is all about making sure that you don't get bad sort of transient behaviour. And we also left off last time with this different type of integral constraint now in the frequency domain, right, which tells you that if you try to push the output sensitivity function down at low frequencies, okay, in order to get better reference tracking, okay, or better output disturbance rejection of low frequency inputs, then it'll cause the sensitivity function to pop up somewhere else, giving you worse performance there. Okay, you can think of where the sensitivity functions pop up. All right, the complementary sensitivity function will be something like this, and if it's popping up, which it'll always do if the output sensitivity function pops up, it's like you might be pushing the crossover frequency to the right to make things faster, but then this starts happening, right? And as you keep pushing it further to the right, it keeps on peaking up. What we can think of the output, the complementary sensitivity function T, in terms of second order dynamics, right? And if you have something that rolls off like this without peaking up as a second order system, then this frequency where it starts to roll off tells you about how fast the transients die away in a step response. Okay, whereas and so that might be a situation where you have open loop poles like this, and you start increasing the gain. This pole moves this way, this pole moves this way. As we're increasing the gain, moving this one this way and this one this way, we're making things faster. We're pushing the roll-off for the complementary sensitivity function further to the right, okay? But you've got to be careful with this intuition, because in a situation like this, if we keep increasing the gain, the poles meet and then split apart, and when they split apart, they stop becoming faster, but you just get this peaking, right? Which is why we're, looking at things like this to figure out when there might be peaking, right? Because that's going to tell us about, when increasing the gain further is no longer going to make it faster, right? Because as the closed loop poles are moving up here, the real part's not changing, so it's not getting any faster, right? But we're getting more oscillations in the response, okay? So that's why we might avoid peaking in the sensitivity functions as we're trying to get faster by increasing the gain of the loop transfer function. So if you look at the loop transfer functions, to get this one here at this crossover frequency, the loop transfer function would look like that. By increasing the gain everywhere by the same amount, it moves to there, then it moves to there, right? And we keep on increasing the gain. We're always increasing the crossover frequency, but beyond a certain point, we stop making things faster, and things just get more and more oscillatory as we increase the gain. So, that's the point of doing all this sort of analysis, right? So that when we do design and try things out, we're able to interpret what the outcome is, right? And understand what's causing what, all right, in order to make further adjustments to get what you need in the end. All right, so what we're going to do today is see another application of these so-called interpolation constraints that's more closely related to this, but for now more sophisticated input signals at the reference and the disturbance inputs. Okay. So, you know, we often think about the performance of a control system in terms of its response to particular classes of reference and disturbance signals. Okay. You know, sometimes we don't know that much about the reference and disturbance signals, and we might just know how the energy is distributed across a band of frequencies. But sometimes you know more about the signals than that. You might know that the signal is a step or a ramp, and you just don't know what the constant is. Or you might know that it's a sinusoid of a particular frequency, but you don't know the phase and you don't know the magnitude, rather than it just being an arbitrary signal that can wander around that has its energy distributed across frequency in a particular way. And so if that's the case, you want to try to exploit that extra information. All right? So let's think about how we can describe the sorts of signals that I mentioned: steps, monomial signals, so things like ramps, or just a quadratic signal or a cubic signal, or sinusoidal signals, right? Well, we can describe such signals in terms of the solution of an autonomous ordinary differential equation, right? So the solution to this differential equation with an initial condition x bar, right, is a step of magnitude x bar, okay? And if we took the Laplace transform, right, what would we get? We would get s x s minus x at naught equals 0. Okay, so all I've done is taken the Laplace transform of that, accounting for the initial condition, right? So you're getting x s s is x naught divided by s, and we're saying that x naught is x bar, right? And we know that this is the Laplace transform of a step. Okay? If we look at this, right, then what we get out as a solution with this as these as the initial conditions is a ramp, right? And the slope of the ramp is determined by the initial condition for x dot, right? So you can verify that by just direct substitution, okay? The initial conditions are satisfied, right? At 0, this is 0, okay? If I look at the derivative of this, it's just x bar, so at time 0, that will be true, right? And if I then took the derivative again, I would get 0, so it satisfies the differential equation. If I just take the Laplace transform of this, what do I get? I get s squared x s minus s x naught. So these are big x's and these are little x's, right? Minus x dot naught equal to 0. Okay, and so we're saying that this is 0 and this is x bar, and so we're saying x s is x bar on s squared, which we know is the Laplace transform of a ramp. Okay, and you can do similar things to describe sinusoids. So a sinusoidal signal that looks like this will satisfy this differential equation with these initial conditions, right? And you can go through the same process, taking the Laplace transform, you get s squared x s minus s x naught minus x dot naught plus omega squared x s equal to 0, right? And if you rearrange that, you get x s is s x naught plus x dot naught divided by s squared plus omega squared, which looks like the Laplace transform of cos, right, when x naught is x bar, right, and this is 0, or sine. Okay, so more generally we can describe interesting signals, and what's interesting about these signals is that they persist. They don't die away, and so there will be a steady state response to these sorts of signals, right? That won't be 0. And we assess performance often in terms of the steady state response to these things, right? If we want to track a reference, we know that with feedback control, it's not going to happen instantaneously. We're going to approach the reference asymptotically, and we want to make sure that the error is small in steady state. The same goes for rejecting, for example, a periodic disturbance. Okay, so more generally, we can describe these sorts of signals that persist using higher order differential equations, right, with a set of initial conditions. Okay, just like in the examples here, if you take the Laplace transform of this autonomous ordinary differential equation with initial conditions, you get an expression like this for the solution in the Laplace domain. Okay, so we get a polynomial on top that will be degree 1 minus the order of the differential equation, just like here we got an order 1 for a second order differential equation. All right, and on the bottom we'll get something that's called the generating polynomial. So the generating polynomial is determined by the coefficients here, right, whereas the polynomial on the top, which is degree 1 less than the generating polynomial, is determined by the initial conditions. All right, and for the signal to persist, right, this generating polynomial must have roots on the imaginary axis. Okay, so if we look at this, it has a root at s equals 0. So the generating polynomial here is s. That's the generating polynomial for a step, and it has a root at s equals 0. For a ramp, it has 2 roots at s equals 0. For the sinusoid, it has 2 roots at plus and minus j omega. Right? The value of s that makes this equal to 0 is plus or minus j omega. Right? So signals persist when the roots of the so-called generating polynomial on the imaginary axis. Okay. So let's consider a reference generating polynomial and look at it in this factored form, okay, where each of the roots are on the imaginary axis. In other words, the real part is 0. So this will correspond to a reference that persists, right? And we're interested in understanding the steady state response to this signal that doesn't decay to 0, it persists, right? If it's a sinusoid, it persists in a bounded way. If it's a step, it persists in a bounded way. If it's a ramp, it persists in an unbounded way. Okay. So if we look at tracking performance for a reference that looks like this, so a reference that's associated with this generating polynomial, then we know that the output will be the complementary sensitivity function times the reference, okay? The error signal, all right? So let me just remind you what the closed loop looks like. Got the controller, we've got the plant, okay? There's Y, there's E, there's R, okay? So we know that the mapping from here to here is the complementary sensitivity function. The mapping from here to here is the output sensitivity function. So the error signal is the output sensitivity function times the reference, right? And U is this signal here, and there's a corresponding sensitivity function for that, which is just C times S, okay? Now, if all the roots of the generating polynomial, so these numbers, gamma n, are poles of the open loop transfer function, that is the product of the plant and the controller transfer functions, then from the interpolation constraints that we saw before, we know that the output sensitivity function evaluated at the roots of the poles, open loop poles, will be 0. Okay, and as before, that suggests that the output sensitivity function can be factored in the way shown here. Right, so before, when we just had an open loop pole at s equals 0, the fact that we were pulling out the front was just s, right? And that corresponds to gamma n being 0, right? But more generally, if the gamma n's are all poles of the open loop transfer function, then the output sensitivity function will have factors like this that we can pull out the front, right? So the numerator of this s hat function here will be of degree less than this, right? It will be of degree q less than the degree of the numerator here, but it has the same poles, right, as a transfer function. All right. So if we want to know what the error looks like, then it will look like this product of the S minus gamma n's, S hat S times the reference, and the reference is this polynomial psi divided by the reference polynomial. Okay? So these guys cancel each other out. Just like back here, the S's cancelled each other out, right? Leaving us with the Laplace transform of the error signal being given by this function here, right? And if the closed loop is stable, right, then this function is well defined in a right half plane that contains the imaginary axis, which tells you that this is a signal that in the time domain decays exponentially to 0. All right? So it's just a generalization of what we saw for the step, right? So really, what we're saying is that if the generating polynomial roots are made poles of the controller, right, or if they are robustly poles of the plant, okay, then we will get 0 steady state tracking error. Okay? And this is called the internal model principle. Okay? The way to ensure that you have these roots of the generating polynomial as open loop poles is to make them poles of the controller. Right? You can always do that. The controller is what you're designing. You're choosing it. Right? So if you want to track a sinusoid, right, you know what its generating polynomial looks like. It's this guy here, right, given that you know the frequency. And, in order to get 0 steady state tracking error, all I have to do is make sure that the controller that I'm designing has poles at plus and minus j omega. Okay? But sometimes the roots of the generating polynomial will be robustly part of your plant model. Like if your plant model already has an integrator in it, right, just by virtue of the dynamics of the plant, then to track a step with 0 steady state error, you don't need to add a pole to the controller because you've already got it in the plant. And this result is based on the open loop transfer function having poles that coincide with the roots of the generating polynomial. Okay. In the case that the input is a disturbance to the plant rather than the reference, you have to be a little bit more careful. Okay, so this is a generic setup, right, that corresponds to input disturbance when this is equal to 1 and this is equal to the plant transfer function, and it's equal to an output disturbance if this is 1 and that's the plant transfer function. So it's just a generalisation of the standard feedback interconnection that we've been looking at. Performance of this closed loop from the perspective of disturbance rejection is about how sensitive this signal is to the disturbance, right? So you can work out what the transfer function is from here to here, right? The transfer function from here to here will just be the output sensitivity function, right? Just like the transfer function from here to here is the output sensitivity function. Whenever you've got a signal coming in through a summing junction like this, then from the input to the output of the summing junction in closed loop will always be the output sensitivity function, just like here, all right? So this signal here will just be the output sensitivity function S0 times G0. Okay, so how sensitive this signal is to D is just given by this transfer function here. Okay, we might also be interested in how sensitive this signal is into D from the perspective of actuator saturation and rate limits and so forth. Okay, and the transfer function from D to here is given by this, where this is just C times this here. All right, and you can re-express it also in terms of the complementary sensitivity function. As an exercise, if you can't see this straight away, go and work it out. right? It's just, we've seen how to get transfer functions from inputs to internal signals lots of times, right? You just read the equations off the block diagram and manipulate them to find the corresponding relationship. Okay, so if we know something about this and we know how to describe this signal in terms of a corresponding reference generating polynomial in the way that we just saw, then if all the roots of the reference generating polynomials are made poles of the controller, or if they are robustly part of the input part of the plant, this guy here, all right, then, when you replace this by some polynomial divided by gamma, right, then the gamma will cancel out with the fact that by making the open loop have poles at the gamma ends, you'll have factors that you can pull out of S in the way that we saw here, and they will cancel out, all right, just leaving you with a function that is well defined in a right half plane that contains the imaginary axis, right, which means that in the time domain that signal will decay to zero exponentially. You can't rely on the roots of the generating polynomial being poles of the output part of the plant, right? Okay, because if they were, then they would get cancelled out by the factors that you can pull out of S in the way shown here, and you would be left with these things on the bottom from substituting D by some polynomial divided by this. All right. So again, basically the way to apply the internal model principle is to put the poles in the controller. Put the roots of the generating polynomial as poles in the controller. Then you don't have to rely on them being in the plant robustly, right? Or worrying about whether or not they're in the input part or the output part of the plant model. Okay, so we've already seen an example of this back here. In this example, right, where in order to reject a disturbance that's not completely unknown, we know something about it. We know that it oscillates with the frequency of 1 radian per second, but it's still uncertain in the sense that we don't know its size or its phase. And the way to deal with that was to put this in the controller, right? So the generating polynomial of a sinusoid of frequency 1 is s squared plus 1, right? And we put that in there. And when we were looking at this example, we understood the rationale for doing so in terms of getting infinite gain in the open loop transfer function at the frequency 1, okay, which makes the input disturbance sensitivity function, which tells you about how sensitive the output signal is to an input disturbance, 0 at that frequency, right? Which is what you need to get 0 steady state rejection of that disturbance. So we've just put a bit more meat around that by looking at this stuff here. Okay. All right. So this is just trying to summarise how to apply the internal model principle. Okay. And just make the roots of the generating polynomial poles of the controller. In the case of an input disturbance, note that the complementary sensitivity function, all right, will be 1 at the open loop poles, right? If we're making the open loop poles coincide with the roots of the generating polynomial, then t will be 1 at the roots of the generating polynomial, right? And if we go back and look at this, in the case of input disturbance, so this guy being 1, right, what you can see is that this becomes 1 at the roots of the generating polynomial, all right, provided we make those roots open loop poles by, for example, putting them in the controller. And you can see that u in steady state will then just be minus d. And what's happening is that the control system is reproducing the disturbance, okay, minus the disturbance, so that they cancel out, and you'll put 0 in here and you'll get 0 out. Okay, making this as insensitive as it can be to this signal here. You can't be more insensitive than being 0 when you've got this input trying to wiggly push you away from 0. Okay, so this is a very powerful principle. Okay, it's robust if you put it into the controller, all right? It's robust in the face of modelling uncertainty as well, because we've seen that the sensitivity function of the perturbed closed loop, when you replace the model of the plant by another model that includes multiplicative modelling uncertainty, is just the product of the unperturbed sensitivity function and another function. What we're doing with the internal model principle is making sure that this has zeros in the right spot. We're making sure this has these factors so that it'll cancel out the gamma, right? And that will happen robustly, right? Because the perturbed closed loop in the presence of multiplicative plant modelling uncertainty still involves that function there, okay? That shouldn't be surprising, right? Because we can force, this to have zeros by just making the controller have the right poles, right? Okay, you got to be careful doing this though, because by having imaginary axis poles in the controller, you're using very high gain feedback, right? The pole, the controller at that frequency has infinite gain. So any any measurement noise coming through will get amplified, right? So you've got to make sure that that's not the case. Effectively what you're doing is you're putting open loop unstable poles in place, right? Poles on the imaginary axis are unstable. And in the analysis that we saw last time, we saw via the integral constraints on the error signal that you need to make sure that the closed loop is sufficiently fast, right, in order to get reasonable transient behaviour when you have open loop unstable poles. And now we're putting open loop unstable poles in to get, steady state performance, right? And in order for the closed loop to give you reasonable transients, right, we need to make sure it's fast enough. And to get it fast enough, you might need to pump up the gain of the controller to push the crossover frequency to the right, which might lead to other problems like actuator saturation and things like that. So you've got to use this with care, right? Understanding the implications of it, right? And in part that's why we looked at these sorts of limitations of having unstable poles, because you might be putting them in there. They may not be part of the plant. You're putting them in there, right, in order to meet these steady state objectives. Okay, so you've got to be careful using this sort of stuff. All right. So, so far we've focused on only having one degree of freedom in the design of a feedback control system. Okay, that is the controller. Okay, and what we're trying to do is use that one degree of freedom to shape 4 sensitivity transfer functions, right? And that's what leads to these trade-offs. Okay, but we saw right at the beginning of part 3 that we can introduce an additional degree of freedom, right? By having, for example, a pre-filter for the reference signal. Okay. So if we go right back to the, if I can find it, right back to the beginning, there we go. We saw that you could get an extra degree of freedom to help you meet reference tracking objectives by having a pre-filter for the reference here. Right, so it just gives you an extra degree of freedom so that the transfer function from the reference to the output signal is not just the complementary sensitivity function, it's the complementary sensitivity function times this pre-filter. Okay. So that extra degree of freedom can be exploited in control system design in a way that corresponds to like open loop control, where you're effectively inverting the complementary sensitivity function. Okay, to improve your reference tracking performance. Okay, so with this extra degree of freedom in place, the output signal will not just be the complementary sensitivity function times the reference, right? It'll be the complementary sensitivity function times this pre-filter times the reference. The error signal will now look like this, rather than just being 1 minus t times the reference, and so on. Right? So the essence of reference feed forward is to use this filter to invert t, right? Because if I make that 1, then I'll get perfect tracking, right? But you're not going to be able to invert t exactly, right, everywhere. And part of the problem is that you need this filter to be have a proper transfer function, right? And so in order for it to be implementable, causal, if you like, all right? And so you can't just invert t at all frequencies, right? You might just do it over a band of frequencies where the reference has significant energy. And the other thing you've got to be aware of is that, you know, perturbations to the models you're using will change T naught, right? And so your inverse will be sensitive to modelling errors, okay? The other thing is we need H to not just be proper, we need it to be stable, right? Because we're putting that on the reference, right? And if we're putting steps and bounded signals in here, and this is unstable, we're putting stuff into the closed loop that's blowing up, right? And we, you know, even if the closed loop is stable, we wouldn't expect the internal signals to remain bounded, right? Even though we're trying to get it to track this, okay? So these are all the limitations associated with using this pre-filter, but really what we're trying to do is make this transfer function 1 to improve the tracking performance via this extra degree of freedom. Okay, so this is just a little example of, you know, a situation where you may not, where you may have to use such a filter in order to meet performance specifications. Okay, because of competing objectives stopping you from achieving the reference tracking objective just with a feedback controller. All right, so we've got a plant here that looks like this. We want it to follow a reference that looks like this. So there's a sinusoidal component of the reference, right? Known frequency, run radian per second, known phase, but uncertain magnitude. Okay, we've got a step component of the reference. We know it's a step, but we don't know how big it is, right? And then we've got this other component, which we don't really know very much about, right? Other than it has energy across this frequency band. Okay, and we're trying to track this reference when we're using a sensor that introduces measurement noise above 3 radians per second. And here's an example of where we can't split the competing objectives across frequency, right? In the sense that we want to be able to track up to 5 radians per second. So we want the complementary sensitivity function to be close to 1, all the way up to 5 radians per second, and preferably a bit further along, right? But then we've got this requirement telling us to make the complementary sensitivity function roll off before 3 radians per second, right? So we can't have it being 1 up to 5 and beyond and rolling off before 3 at the same time, right? So what you can do is design the feedback controller to make sure T rolls off, right? To reduce the sensitivity to measurement noise that becomes significant after 3 radians per second, all right? And then use the pre-filter H, right, to extend the range of frequencies across which the transfer function from the reference to the output is 1. Okay, this with the pre-filter in place is the transfer function from the reference to the output. Okay. Now, to get zero steady state tracking error for this part of the reference and this part of the reference, we just need to, by the internal model principle, make sure the controller has a pole at s equals 0. That's the generating polynomial for this guy. And s equals plus or minus j. That's the generating polynomial for this guy. All right, so here's a feedback controller. It has the pole at s equals 0. It has the 2 poles at plus or minus j. Okay, this guy cancels the stable plant poles. Okay, I know a lot of the examples do this, I'm just taking these examples from the Goodman book. You don't always have to cancel the open loop poles, right? But by cancelling the plant poles, right, what you're left with is just the controller transfer function, and you just make that have the right shape to give you the lambda that you want, right? Because once you've cancelled the plant poles, then everything is in your control, right? So that's the rationale for doing that, but you don't always have to do that. And then we're introducing 2 extra zeros and something that rolls off, okay, to make sure that the complementary sensitivity function will be less than 1 at 3 radians per second, okay? So this gives us this complementary sensitivity function, right? It's shown on this page here, so you can see that the nominal complementary sensitivity function, it does this. It's 1 over a reasonable range of frequencies, then it starts to wobble about a bit, but it definitely rolls off beyond 3 radians per second, okay, in order to give us low sensitivity to the measurement noise. All right. Now, what we're going to try to do with H is this. We want T times H to now be extended flat and then roll off only beyond 5, well beyond 5 radians per second in this case, right? Here's 10, right? Really pushing it out. So we'll definitely meet the specification associated with tracking this part. All right. If you look at the complementary sensitivity function, it has relative degree 2. Because we're restricting H to be a stable and proper transfer function, the product of these two things will have to be relative degree 2, right? Or relative degree 3 or more, right? If this is proper but not strictly proper, then the product of these two things will be still relative degree 2, right? So we're not going to be able to make it 1 everywhere, but we can choose to make it something that looks like this, so that it's flat over a very wide range of frequencies, and then we're controlling where it's rolling off here. And we're controlling where it's rolling off here by using these to cancel these, and then we're inserting that there. Okay? So we're using this to define what the product looks like in the end, and the rest of it is about cancelling these out, inverting them, in other words. Okay? All right. But that's the basic idea, right? But you've got to be careful using this, because what we're doing is inverting a model, and the model will be wrong, and so your inverse will be wrong, and you won't get exactly this flat thing when applied to the real system. But it is a way of introducing an extra degree of freedom to help you manage a trade-off between competing objectives that can't be completely separated across frequency, put into different frequency bands. Okay. So this idea can be extended to the situation where you can measure the disturbance. I mean, you can always measure the reference because that's your way of commanding the system, so you know what the reference is. Sometimes you can measure the disturbance, right? And so you can introduce an extra degree of freedom in this path here, which is, again, like open loop control, right? If we now look at the transfer function from this disturbance input to the output, you see that the output depends on the disturbance input via this modified transfer function now. And if you can choose this feed forward path to invert this, or make the product here effectively -1, then you get 1 minus 1, that'll be 0. And it's like making Y completely insensitive to D. Okay, but again, you've got to be careful. This feed forward path has to be proper. It has to be stable, right? So that you don't end up with signals that blow up here, right? And so that limits how you can do this inverse, okay? And this is just a little example that shows you, again, where there's something that's stopping you from, pushing the crossover frequency to the right, which causes the sensitivity to peak up, right? Because we've got an unstable pole, okay? That means that, the output signal is very sensitive to an input disturbance at the right frequency, at frequencies around here. Okay, so this is with no disturbance feed forward, but if we can measure the disturbance and pass it through a feed forward filter that tries to make this equal to -1 so that this is equal to 0, you can get much better performance. Okay? But again, you've got to be very careful. You're inverting a model. Your model is wrong, and so your inverse will be wrong. But what we're doing here is not just inverting an open loop model, we're inverting things that, well, in this case we are, but in this case we're inverting a closed loop model. And part of the reason for closing the loop around a model is to make the closed loop less sensitive to modelling error, right? So you'll know this with more certainty than you know the plant model, especially over low frequency ranges where we may have pumped the gain of the open loop transfer function up high, which will force T to be 1 over a wide range of frequencies up to the crossover frequency. So you do know T pretty well, at least over low frequencies, and so you can safely invert it, frequencies around there. All right, so that's the basic idea of feed forward. It's just a way of putting an extra degree of freedom in place. Okay, so this is just a summary of the main points. Okay, in part B of section 3 here. So part B started off with thinking about closed loop relative stability, right? And it's really about measuring how close the Nyquist plot gets to the point -1, right? If the Nyquist plot sits on -1, then you have closed loop poles on the imaginary axis. Okay, if you're close to -1, you're going to get closed loop poles that are close to the imaginary axis. You're going to get oscillations in the transient part of the response. You're probably going to have peaks in your sensitivity functions. Okay, so being far away from -1 is a good way of getting good transient performance. Okay, we saw how we can account for modelling uncertainty, and in particular we looked at multiplicative modelling uncertainty. We saw that in order to be robust to multiplicative modelling uncertainty, which is typically most significant at high frequency, we just need to make sure that the complementary sensitivity function is small at those frequencies. In other words, the open loop transfer function has to have a small gain. All right? We've seen some limitations, and then we've seen today a very important principle called the internal model principle, which is about steady state performance. Right? So these integral transforms, integral constraints that we were looking at on Friday last week were more about the transient stuff, right? Whereas what we're looking at today is about nailing steady state performance objectives, right? By just making sure that the controller has poles in the right spots, right? The controller has to have poles at locations that coincide with the roots of the generating polynomial. If you do that, you can robustly achieve steady state performance objectives, okay? And we've just seen how to incorporate an additional degree of freedom to help you in situations where you can't separate the competing objectives into different frequency bands. Okay, but you've got to be careful because that's the feed forward part here is like open loop control. And open loop control can be sensitive to modelling errors. All right, so tomorrow we'll start looking at part 4 of the notes, which is really about design. We've done a lot of analysis now. We're going to start, we've done some design. Now we're really going to look at design. And then on Friday, we'll look at problem set 4.
For example, we have the step function can plot with the zeros as.
If I've got a function, right, that is equal, so I've got a function, right? And if I know that this is equal to 0, then that implies that S, you can factor out an S. It's got a factor that is S minus 0. Right? It's like if I could say if that is equal to 0, it implies that S must look like S minus X times something else.
Yeah.
Make sense?
Yeah, makes
Right?
sense.
So that's all we're doing. So instead of just doing it at 0,
Yeah.
right, we're saying, well, if we know that our reference looks like this,
Generation.
right?
Yeah.
And if I know that I can do this,
Yeah.